Welcome to the fifth video lecture in discrete mathematics. This will be the last video in the introductory week. So in this video, we will be introducing you to the notion of elementary number theory and its notations. We will be using number theory for various problems in the following lectures, and that is the reason this introduction to number theory is very essential. Now, number theory is something that all of us have used or seen in our high school or colleges. We have seen integers and we have seen divisions. So let's start with this simplest operation that we have learned. Namely, if you are given two positive integers a and b, then we say b divides a if a can be written as b times q, where q is some positive integer. The notation that we use to denote it is this notation, which means b divides a. Now, if a does not divide b, it is denoted using this notation a with a vertical line and striked out b. So it reads as a does not divide b. Now here is a small exercise. Namely, this relation a divides b proves that it is reflexive and transitive. Also show that this relation is not symmetric. This will also help you understand the notion of relations that we have described in a previous video better. Now, in this video, I have made some few observations. These are pretty standard observations in number theory, but for completeness I have written it down explicitly and we will be going over it one by one. Here is the first one. If a, b and p are three positive integers such that p divides both a and b, that means p divides a and p divides b, then we can show that p divides a plus b. So let's see why is this true. Note that all these things should follow from the basic definition of division. So to start, since p divides a, this implies that a can be written as p times r for some positive integer r. Similarly, since p divides b, b is equals to p times s for some positive integer s. So what is a plus b? So a plus b is p times r plus p times s, which is of course p times r plus s. Now, since r is a positive integer and s is a positive integer, this means that r plus s is also a positive integer. In other words, p divides a plus s. Sorry, p divides a plus b. Because a plus b is written as p times r plus s, where r plus s is a positive integer. It's a very easy observation that follows from the basic definition of division. Now let's move on to the next thing. This is again something that we must have seen in our elementary school or middle school. That is the notion of remainder. So if a and d are two positive integers, then a can be written as d times q plus r, where q is an integer, positive integer, and d is also a positive integer. but r is strictly less than d. Note that there is a unique way of writing a as dq plus r, where r is strictly less than d and r is a positive integer. When we can write it this way, we say r is the remainder when a is divided by b. Just a quick comment. If r is equals to 0, that means if the remainder is 0, in that case what happens? In that case a is equals to d times q, where q is a positive integer, or in other words a is divisible by d. So thus if d divides a, then the remainder is 0, else we get a remainder that is less than d. Also, one more observation to do is that since a can be written as dq plus r, that means a minus r is dq, which also means that d divides a minus r. Here is another way of writing the remainder. So if d divides a minus r, where r is a positive number, positive integer less than d, then d is the remainder when a is divided by d. Now, to represent this notion that when a is divided by d, the remainder is r, we use this following notation. A is congruent to r mod d. The way to read it is a is congruent to r mod d, and it means a minus r is divisible by d, or r is the remainder when a is divided by d. Okay, so it reads as d divides a minus r. Just a comment. This notion of modulus, mod, doesn't necessarily need r to be strictly less than d. In fact, if d divides a minus r, then we can write it as a is congruent to r mod d. We will be using this notation quite often in the code. Now, this is something I just now spoke about. If a and b are two positive integers, then b divides a if a is equals to b times p for some integer p, for some integer q. And if b does not divide a, that means a will, when divided by b, surely has an integer that is not equal to 0, or I get an r which is greater than equal to 1 and strictly less than b. So if we get a remainder which is non-zero and between 1 and b, then it means that b does not divide a. So this brings us to the second observation, namely, if a, b and p are three positive integers such that a is divisible by p and b is not divisible by p, then p does not divide a plus b. So let's see the proof of this. It's again and follows from the standard definition of remainder and divisibility. So p divides a implies a is equals to p times r for some integer r. Now P does not divide B, that means B can be written as P times S plus T for some T which is greater than or equal to 1 and strictly less than P. So what is A plus B? A plus B equals to PR plus PS plus T, which is P times R plus S plus T. Again, here it is, so we can see that A plus B equals to P times R plus S, which is a positive integer, plus a number T, which is a number which is by the definition of T greater than or equal to 1 and less than P, or in other words it is not 0. So by the definition it shows that P does not divide A plus B. Now let us see the third observation. So if A, B, P and Q are 4 positive numbers, so there is a mistake here, it is not 3, it's 4 positive integers, such that A is divisible by P and B is divisible by Q, then we would like to show that PQ divides AB. Again, it follows from the first principle. So here is the proof. So P divides A, that means A is equals to P times R for some positive integer R. Similarly, Q divides B, that means B is equals to Q times S for some positive integer S. So A times B equals to PR times QS, which is PQ times RS. Now since R and S are both positive integer, R times S is also a positive integer, which means that AB is divisible by PQ. So this gives us 3 observations in number theory. Moving on, let us see one of the most crucial and beautiful concepts in number theory, or the beauty in numbers, namely prime numbers. So we say that a positive number P is a prime if no number or no integer lesser than P divides P. So for any x which is bigger than 1 and less than P, it is not, that does not divide P. So in other words, you can check or prove for yourself that a number that is not prime is divisible by some other prime. So what are the examples of prime? So 2 is a prime, and it is in fact the only even prime that we have. The other primes are 3, 5, 7, 11, 13, 17, 23, 29, 31 and so on. Here is another observation that is there. We have not proved it here, but I leave it to you guys to check it or verify it. If A and B are 2 integers such that P divides A but does not divide B, then P does not divide A plus B. So this brings us to the short video of introducing you to the subject of number theory. I encourage you guys to quickly revise your high school or elementary notes on number theory, numbers, prime numbers, divisibility and so on. We will be spending some time on number theory in the next 2 weeks. I end this video with 2 problems. Problem 1 is that if A and B are 2 positive integers, then prove that A square minus 4B cannot be equal to 2. So irrespective of what a and b are, as long as they are positive integers, a square minus 4b cannot be equal to 2. So in other words, in the notation of modulo, we would like to say that a square or any square of any integer a cannot be congruent to 2 mod 4. Again, this should be read as a square minus 2 is not divisible by 4. We will be solving this problem in the next week. The second problem that we have is, if p is a prime number, prove that the square of the prime number is always congruent to 1 mod 6 when the prime is bigger than or equal to 5. Or in other words, if p is a prime number bigger than or equal to 5, then p square minus 1 is divisible by 6. So these are two very beautiful and easy problems. The first problem says that the square of any integer minus 1 cannot be divisible by 4. And the second one says that for any prime bigger than or equal to 5, the square of the prime minus 1 is divisible by 6. So this tells us some beautiful facts about integers. Since this was the first week of this course, I have given only introductory lecture videos on various topics. From next week, we will start on solving problems using various techniques and so on. Thank you.